The isocyanate sulforaphane has generated over 3,000 preclinical publications over the last 3 decades, largely due to its potent chemoprotective properties in animal models. Yet, when we review the dozens of human clinical trials attempting to replicate these effects, the data becomes noisy. Outcomes that were definitive in mice routinely register as statistically insignificant in human populations. This inconsistency stems from a flaw in clinical trial design rather than a failure of the molecule itself. To bridge the gap from animal models to human efficacy, researchers must navigate a strict 3-part pharmacokinetic bottleneck: the kinetics of prodrug conversion, immense microbiome variability, and severe errors in allometric scaling. Direct, precise clinical results in humans requires researchers to stop treating this natural product as a casual dietary supplement and start treating it with the strict pharmacological exactitude applied to synthetic drugs. A common misconception in clinical nutrition is that broccoli contains sulforaphane. In the undamaged plant, there is virtually no free sulforaphane. Instead, the plant stores it as a highly stable, biologically inert precursor called glucoraphanin. Converting this inert precursor into active sulforaphane requires the catalytic intervention of a specific beta-thioglucosidase enzyme known as myrosinase. Standard human preparation of cruciferous vegetables, whether through boiling, microwaving, or processing into commercial extracts, completely denatures and destroys this delicate plant myrosinase. Consequently, when human subjects ingest pure glucoraphanin supplements or cooked broccoli, they are consuming a biologically inert prodrug that has been completely stripped of its mandatory activating enzyme. This schematic maps the 3-stage biosynthesis of glucoraphanin inside the plant's chloroplasts. The process begins with the elongation of the methionine amino acid side chain. Following that, a cytochrome P450-mediated conversion forms the core structure, culminating in an S-oxygenation reaction catalyzed by a flavin monooxygenase. This final step yields the complete, stable glucoraphanin molecule. Evolutionarily, the plant maintains a strict physical separation between the inert glucoraphanin and the activating enzyme myrosinase, storing them in distinct cellular compartments. Only direct physical injury to the plant tissue, such as chewing by a herbivore or crushing during food preparation, can breach this internal barrier. Once the cell walls rupture, the two molecules collide. The myrosinase immediately catalyzes the hydrolysis of the precursor, liberating glucose and creating an unstable intermediate that rapidly rearranges into highly reactive sulforaphane. In nature, the sulforaphane molecule is a highly volatile chemical defense mechanism synthesized exclusively in response to sudden cellular destruction. Because mammalian cells do not produce myrosinase natively, a human ingesting the enzymeless precursor relies entirely on the bacterial microflora in their gastrointestinal tract to perform the conversion. This graph charts the stark pharmacokinetic differences between active and inactive formulations. When subjects ingest pure, preformed sulforaphane, we see curve A, a rapid, predictable plasma spike reaching approximately 2 micromolar, followed by a swift clearance via the mercapturic acid pathway. Curve B represents the ingestion of pure glucoraphanin. Without the plant enzyme, the absorption profile flattens into a wide, delayed, and highly unpredictable trajectory. This translates into massive clinical noise. Depending on the specific composition of a subject's gut flora, their urinary excretion of sulforaphane metabolites from a glucoraphanin dose can range wildly from 1% to 40%, segregating the data into distinct clusters of high converters and low converters. Relying on unformulated glucoraphanin ingestion effectively outsources dosing control to unpredictable gut bacteria, guaranteeing inconsistent trial data. The second major factor distorting the clinical data originates in the preclinical literature, where we find a systemic design bias in rodent models. This scatterplot of animal trials reveals that the median effective rodent dose is 113 micromoles per kilogram, overwhelmingly delivered via intraperitoneal injection. This delivery method utilizes a physiological cheat. By injecting the compound directly into the peritoneal cavity, researchers completely bypass the gastrointestinal tract, entirely sidestepping the human microbiome conversion bottleneck. This creates an immense translation wall. Human trials utilize oral dosing, typically capping maximum safe administration between 1.5 to 3 micromoles per kilogram total per day. Attempting to brute force human trials by simply scaling up to match rodent doses introduces serious risks. In specific chemical carcinogenesis models, high-dose post-induction treatment with sulforaphane paradoxically promoted tumor growth and increased tumor size. The molecule has a narrow therapeutic window. The lethal dose for half of the tested population sits at 1,203 micromoles per kilogram, with lower high-dose brackets causing severe sedation, hypothermia, and impaired motor coordination. Preclinical intraperitoneal data provides a mathematically misleading roadmap for human oral efficacy, requiring trial designers to rigorously recalculate their approach to clinical dose delivery. When clinical researchers strictly control for these variables and optimize the formulation, they achieve definitive, measurable pharmacodynamic success. We can observe this precision in multi-dose, placebo-controlled trials conducted in the Qidong region of China. To bypass the conversion bottleneck, researchers administered a highly specific formulation, a standardized beverage delivering exactly 40 micromoles of pre-formed sulforaphane and 600 micromoles of glucoraphanin. The pharmacodynamic outcome was unmistakable. Subjects receiving this formulation exhibited a 61% increase in the urinary excretion of mercapturic acid conjugates derived from highly toxic airborne volatile organic compounds like benzene and acrolein. Despite immense pharmacokinetic hurdles, systemic target engagement in humans is provably achievable when the delivered dose is strictly and mathematically standardized. This data matrix charts 50 human clinical trials, analyzing dose amounts on the x-axis against the specific compound delivered on the y-axis. The z-axis registers clinical success. Looking strictly at successful nodes, a singular determining trait emerges. They all explicitly control the conversion bottleneck. Future trial design must therefore follow one of two mandatory formulation pathways. Researchers must utilize stabilized sulforaphane, such as alpha-cyclodextrin encapsulation, or they must strictly quantify the co-administration of glucoraphanin alongside active myrosinase. Continuing to rely on unstandardized extracts and crude dietary assumptions produces data too noisy to yield actionable clinical conclusions. Closing the translation gap demands that the medical community abandon platitudes about food as medicine. We must treat these complex plant-derived molecules with the precise pharmacokinetic rigor demanded by any synthetic drug.